Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
See whether I can switch this on. Or is it on already? Test. Is this amplified? Yes, it is, right? Okay.
And is this live for an introduction? Oh, close enough. At the very least, people here can see me. It's a great pleasure to introduce Halvar Flake, who's one of the best reverse engineers I've ever met. And furthermore, his girlfriend once told me that I have program analysis hair, and so that's a very strong recommendation. So with that, go ahead.
All right, good morning. I'm Halvar. I study mathematics in Germany at the Ruhr-Universität Bochum, which is just a university in Germany, which is badly funded, as all German universities, I guess. And I'm going to speak about structural comparison of executable objects, basically comparing, executables for which you don't have the source. Now, why would anybody want to do this? Actually, there's many scenarios in which the comparison of several executables is quite interesting. First of all, if you ever do closed source security analysis, you run into the situation where you have to, analyze version 4, version 4.1, version 4.2 of the same product. You spend a few months on version 4, a few months later version 4.1 comes out, and you have to see whether it still has the same properties, what did they add, what did they change. So there's a lot of incremental reverse engineering, which is quite annoying because you have to redo a lot of the work, because every time you, start disassembling the binary, you have no function names, you have no variable names, all the type information is gone, and you have to go, through the same process of reconstructing function names, reconstructing types. And, for this it would be very, useful to have several versions of the same executable which you can compare, and you can say, these parts are the same, this is what they changed in the new version, which would save you a lot of time redoing work you've already done. Secondly, high-level language viruses are, the current, the viruses of old were all written, handwritten assembly, polymorphic engines, and these things. Nowadays, the malware analysis people have to deal mostly with massive, huge, self-mailing things which have been written in C++, and which reuse a lot of code, like SOBIG or any of the recent mailing things, seem to not be written in assembly anymore, but in high-level languages. And they're so big that, the virus analysts can't very quickly analyze all of it either. And the virus authors can create variants of the same virus very easily because they have the source code, and then they just change a few lines here and there, change the behavior a bit. But the virus analyst has to go through and reverse engineer the entire virus again. So for purposes of analyzing high-level language viruses, comparing two versions of the same executable would be fairly useful as well. Thirdly, there's the field of analyzing security updates, because Microsoft and other source code, post-source vendors are trying to exploit the same asymmetry in the problem of reverse engineering binaries as the virus authors. Because recompiling the same source with a few small changes is no big deal. But disassembling the same executable, again, is a lot of work. So one of the reasons Microsoft, for example, is not disseminating lots of information about about what security vulnerability they patched is because the implicit assumption is that it's really hard to disassemble or to reverse engineer a security patch to understand what was changed, what was the flaw in the first place. And the general problem is, the general idea is that reverse engineering something is harder than just recompiling it. And this is something, both virus authors and closed source vendors try to exploit. And, in the source code world, we can use something like diff, where you can just see the changes in the source code immediately, more or less. And as such, you can fairly easily reverse engineer or find out what the heck they changed. Why can't you do this on the disassembly as well? Because the disassembly should change in, only a few places, some people might ask. The real issue is that recompiling something will change a lot more in the disassembly than just the few lines of source you changed. I mean, if you add a structure member into a structure, all other structure members which come behind the original structure members will obviously shift, and as such there will be offsets which change throughout the entire binary. And if you add a few lines of code, the compiler might decide to do a very, very different way of allocating registers and assigning registers. So all the registers might change. And then, which is especially an issue here with Microsoft code and profile-based optimization, if the size of basic blocks in the executable change, they might get arranged and aligned in a totally different manner, because the way Microsoft executables are built these days is the basic blocks are reorganized to keep only the important basic blocks on the same page and move everything that's not so important to other pages. So two versions of the same executable, although they have only very few changes between them, might look radically different. So diffing like you do in source code will not work. The other thing is the overwhelming majority of the changes you would find using a standard diff are irrelevant. If you're analyzing code, you're not really interested in somebody adding a structure member usually. You're more interested in changing to logic. You're interested, when you're doing the analysis of security patches, in things like somebody adding an if, somebody adding a range check, somebody changing some checks or some protocol or just some program logic at some point. You're not really interested in somebody changing a single constant. So, I already said most of this. So we're going to cover a more general approach in this talk, one that focuses on the structural property of an executable. We're basically going to neglect the code itself and just try to focus on, well, what is the structure of the executable in terms of the calls to relations and the actual shape of the flow graphs of the individual functions. By this, we will avoid stuff like changing register allocations. Well, we're not looking at the code, so if other registers are assigned, we really don't care. The arrangement of basic blocks and so on will not bother us at all, because we're only looking at the graphs. The graphs don't change, only the position of the blocks does. And we don't care about code optimization like this, or not optimization, but just changes in instruction choice like this, where an LEA is replaced by an add. Stuff that the compiler just does, however, well, when he thinks that something might fit into a pipeline in a different manner or whatever. So we're going to focus just on the structural properties of the executable. We're going to neglect pretty much all the code. So I mentioned before that you're primarily interested in changes to program logic. And in the general way, you can look at a program as a graph of graphs, or as two sets of graphs. You have once the big graph that describes all the calls to relations between functions. Function A calls function B and C, and so on. That's the call graph. And I'm going to use the term call graph for this in the rest of the talk. Secondly, there's individual function flow graphs, because every function in the executable has a flow graph of itself, which means the relation between the basic blocks, which basic block branches to which other basic block in the function. So basically, the program logic is encoded in these two graphs. If you add a single if anywhere, something that changes the program flow in the executable, the function flow graph will change. If you add an if, the flow graph will change. Secondly, if you change a call like an str copy to an strn copy or whatever, the call graph will change. So by looking at these graphs, you should be able to pinpoint all the changes between two executables. Obviously, you will not be able to pinpoint changes when it comes to assignedness of variables and the like, but you'll see the logic changes. All right, so I mentioned before, the program logic is more or less encoded in these two graphs. And the nice thing about just comparing the call graph and the individual function flow graphs is the comparison should be free of false positives. The big issue we have now, or people have had before when they try to diff executables, is that they had a ridiculous number of false positives because of changed register allocations and changed constants and the like. If you just look at the graphs, if there's a change in the graphs, the program has to have changed in a way. Because, well, the compiler is not going to emit more basic blocks or different branches if the code doesn't change. So, yeah.
And the compiler may choose to do a set NZ at one time and may choose not to at all, so that may change the flow graph structure. So I'm not sure I agree with your basic flow graph or call graph or whatever shows you exactly what the program, because that could actually change an optimization level or small kind of branches the compiler could know to flatten out.
It's definitely true that a compiler can flatten out certain branches and small functions. And the other thing is that a lot of compilers, or quite a few compilers, do aggressive whole program optimization these days, where they inline an entire function into another function. So that will obviously change the flow graph of the function quite significantly. But the basic thing is that it's highly unlikely that a function that is not inlined in one build of the executable will be inlined in the next build of the executable. And functions will, like larger functions, are not going to be inlined normally. And the situation where the compiler decides to flatten a branch, I'm not sure whether I'm actually quite sure that if the compiler decides to flatten a certain branch, he will decide so consistently in multiple builds of the same application. Because he should do that at a stage where he's only looking at the one function. I'm not sure, though. I mean, you don't know what people who build compilers will come up with next. Obviously,
So the answer is basically, if you give a patch to source code, use the max function quite a lot rather than doing if. Right?
no, I don't think they'll change anything.
Sorry?
I don't think that would make the analysis harder.
If the length is greater than the function, so do something.
Yeah.
But you knew that the product could do it with max. It's got, Intel gives the exact sequence of academic,
Yeah.
How to optimize away branches with the max function.
Yeah.
Maybe you do all your patches such that you don't generate additional branches.
So you're going to, well, if you manage to fix a complex I think it's quite hard to start fixing security vulnerabilities by trying not to introduce a new branch. Let's just say it this way. Because, I mean, even if you do set NZ, you have to do some sort of decision based on it later on anyhow. And well, it doesn't change the fact that you still have to. All right. Okay. So the big issue is that the comparison will not be false negative free. Occasionally, you will have things that cannot be matched or that change, and well, we won't see them. If somebody just changes the buffer size, if you change the size of a stack buffer from 100 bytes to 500 bytes, we can't see it because we're not looking at the code at all. We don't know the sizes of the stack buffers. If somebody changes a constant, we don't know. If somebody changes the type of a signed int to an unsigned int, we can't see it either. We're not looking at anything. We're not doing any type reconstruction. And as such, there's a significant number of changes you can do without seeing it in the graph. Then again, as soon as you start adding ifs or adding a single branch, that should become evident. The big question is, how do you compare it to a graph of graphs? Well, I mentioned before, the executable basically consists of the call graph, which has a bunch of nodes, f1 to fn, which are all the individual functions. And every fi itself is another graph. So we have a graph of graphs. We have a graph where every node is another graph. The first issue you have to face when you're trying to compare the executables is to generate the call graph statically. And that's not always easy because, well, you have OOP code, you have indirection, you have indirect jumps, and so on. This is the first point where I start to fudge by just ignoring the fact that there's indirect calls. I just don't try to resolve indirect calls at all, because I think I'll still get sufficiently large, well, subgraphs basically, which might not be connected because I ignore all indirect branches, but should be enough for doing the actual comparison. Secondly, I'd have to resolve stuff like create thread, which is obviously transfer and control, but it doesn't show up in the disassembly like just from generating the flow graphs. So the first place where I start to neglect things is I just ignore everything that would require any sort of sophisticated code analysis to resolve. Because resolving stuff like a method call statically is not always trivial. Now, what we want to do first is we want to be able to know which functions in executable A is the same function as the one in executable B. So we want to build an isomorphism, which is basically just a mapping from, well, the set of executables, the set of functions in executable A to the set of functions in executable B. So for each function in A, we can find out which function in B is associated with it or is the same. Now, in the general case, such an isomorphism doesn't exist because there might be more functions in one executable than the other. So we're trying to build an approximation. We do this by creating an initial mapping, basically, an initial stub isomorphism. You can build this in many different ways. You can build this by starting with functions that have the same name, like imports from any DLL will probably have the same name. And you can start doing this as well with functions that have an in degree of 0. Like they're not called from anywhere, which means they're most likely entry points in some way. So you try to match those first. And once you have an initial isomorphism, you improve it iteratively. You have one, and then you can use the information from the isomorphism which you have to, well, create a better isomorphism because you can use those graphs for better matching. Now, how can you, aside from the names, how can you start creating those initial fixed points? Creating an algorithm which goes and matches one function, like the graph of one function, to all the graphs of all possible functions in the other executable is just way too expensive because graph comparisons in general are not cheap. So we use a very, very cheap heuristics here. Step 2, where I start to cheat. We create a 3-tuple which just describes the function in a very rough manner. Basically, it tells you, well, it takes the number of basic blocks in the function, number of edges connecting those basic blocks, and number of calls calling subfunctions. And now you have these two big sets of functions, and you create initial fixed points by looking at those two big sets of functions and looking for matches of the signature where there's only one direct match, meaning if there's 5 functions in executable A and 5 functions in executable B with the same signature, you don't match any of them. You only match them if there's one signature of, I don't know, 10, 10, 5 in one executable and one of 10, 10, 5 in the other. So you create those initial fixed points by the assumption that most functions will not have changed. Well, you'll only map a very, very small number of functions initially. First of all, you're not going to map many of the smaller functions. There's just not so many ways of arranging 4 to 5 basic blocks. So the larger the function is, the more easy it will be for you to find an initial fixed point, because at 80, 90 basic blocks, it's very unlikely to have 2 functions which have the same number of basic blocks at 90 and same number of edges and the same number of subfunction calls. For very short functions, functions consisting of only one basic block, well, obviously you can't create those initial fixed points. It's also clear that having any sort of smaller sets to match initially will help, because the smaller the sets you're comparing, the less likely it is to have a collision of the signatures. So you can do stuff like match all the functions which have the same in degree. Try matching all the functions which have an in degree of 0. Try to find arbitrary criteria with which you can group the functions into smaller subsets which are most likely the same, and then do the matching on them. Once you have the initial isomorphism, you can construct a better one in the following manner. You take a node, or you can take a function, and its match in the other executable. What you do then is you take the sets of all functions called from this matched function. So I'll go to the whiteboard. We have a function here. Well, we have a function here and its match over here, and we know that these two are the same. And then we retrieve the subset of functions which are called from this one. And we retrieve the subset of functions which are called from this one here. And now we have 2 smaller subsets for which we can do the same matching as before. Meaning we compare the signatures. If there's a unique match, we create another fixed point. So you iterate over all existing fixed points and create new fixed points from them by comparing those smaller subsets. This obviously works in the other direction as well, because if you have a fixed point, you can create the sets of all functions calling this one here, and all functions calling this one here, and then match those. So you basically create the initial isomorphism, and then you propagate the fixed points upwards and downwards in the call tree. Now, what happens if we're actually hitting a function that has changed? Because the way this works right now, a single failure to match something will propagate. If I can't match this one in the first place, I can't find all these others. So we need to have some sort of way of associating or finding a match, even for functions that change, that have a different signature, that have a different number of basic blocks, different number of edges, and so on. Now, it's a bit of a trade-off here which you have to do. first of all, you have to be tolerant against changes to a function. But secondly, you have to be very conservative in what sort of match you permit, because a wrong match, like matching two functions incorrectly, will produce further wrong matches and will just make the entire analysis a lot less accurate. So we want to stay conservative when it comes to matching changed functions, but still be tolerant to the change. Now, if somebody knows a good measure of graph similarity and an efficient algorithm of measuring it, please do tell me. Because if we had a measure of graph similarity, we could just take the functions which are not matched, like we could take those subsets there, and then measure the similarity of the graphs and take the one that's the most similar function. Now, I don't think that there is a smart way, or I don't know of a quick way of measuring the similarity of two directed graphs in an efficient manner, or efficient enough for my purposes, because I only have a small computer. So, we're going to use a cop-out again, we're going to cheat again, and we're going to try to use the existing isomorphism to narrow down those, well, the matching. So we're fairly conservative in what we're doing there. Well, we can measure the similarity in a very, very simple manner. We got three numbers, so we just calculate the Euclidean distance between them, meaning just we put them into a coordinate system and measure the distance between them. So, but this is too flaky for producing wrong matches, which we really want to avoid. So as a basic measure of the similarity of functions, we use the Euclidean distance, but we want to have smaller subsets than the one generated by this variant here. For this, we create, well, it's just for notation, we have mappings mapping to children and parents of a node. We don't need this. Okay, now we calculate two sets. This looks all mathed up, but in fact it's quite simple. The basic idea is we have a function over here. We have no clue what it is matched to. We would like to find out what are the possible candidates in the other executable that might be the same as this one. Because there's no other function with the same signature. And in order to do this, we retrieve all parents. And check whether any of the parents has been defined as a fixed point, does have a match in the other executable. If it does, we take the match in the other executable. And then we take the sets of children from each one of these. And then we intersect those sets, meaning only a function that is called from all of the matched parents is a possible candidate, which in this case would eliminate this one, because it's not called by all three of them, would eliminate this one, and it would eliminate this one as well. And then we have a set of possible candidates, which are very likely to be the same, and then we choose the one which has the least, well, Euclidean distance in the signature compared to the function we're trying to match. And obviously the same works the other way around. You take the children, you build the match, you go over here, you go upwards again. So,
so if there is no match in the right-hand side of the graph,
if I can't match it at all, no matter what I do at the very end of, I mean, this is an iterative process. If I go through, I have to conclude in the end, if I can't match it, it has either changed so much that it's outside of the maximum Euclidean distance I permit. Because I have the implementation has a maximum distance you can define as a user. And, well, I just say, if it has a match in the other function, that match is so significantly different that I can't match it. Okay, so what do we do now that after we've constructed this initial isomorphism? Once we have the isomorphism, we can start analyzing the changes between the functions. Meaning, We can then go through every fixed point and compare the two graphs and see whether they change in a significant manner. This is a bit more computing intensive, but it's a lot cheaper than comparing one graph to all graphs in another executable, because you only have to match two, of which you already know that they're very similar, all the same. So the second issue, obviously, is detecting changes in the call graph, meaning detecting a change from string copy to strn copy. And that's something you can check for basically iterating through the fixed points and checking whether calculating the isomorphism, like the matching to the other one, and then the children of a function is the same as first calculating the children of a function and then the matching. Basically because, well, I'll try to illustrate again. We have the two functions here, and which belong to a fixed point which we've defined. And we'd like to see whether there was a change in this function where one version is calling something which the other version is not. In order to do this, we calculate the children, or we retrieve the set of children of this function, and match them. And then we take the match and calculate the children, and we see whether these two are the same. So if they are the same, then obviously there's no change. If they're not the same, then somebody has changed a call in some way. Obviously, this is not perfect because there's another change you can do now to a function which we won't see. You can change the order of calls, we won't see it, and so on and so on. But, well. Now, how much time was allocated for this talk? Because I'm just half an hour into it and halfway through, I guess. So practical implementation. I've built a tool, a plugin for a commercial disassembler called IDA Pro, which implements most of the things I've just discussed. The nice thing about staying away from the code and trying to just work on the graphs is that you stay platform independent to a large extent. So right now it supports x86, MIPS, PA-RISC, and PowerPC. I'm going to add more architectures because it's usually 9 to 10 lines of code for adding another architecture. The big exception is platforms with lots of conditional execution. Because the code I have right now just generates a flow graph based on branch instructions which the disassembler has found. And the disassembler doesn't generate the necessary cross-references for basic blocks for conditional execution. So something like ARM or IS64 is a bit more difficult to deal with. Not impossible, just more annoying. There's a little bit of extra code in the plugin which tries to see what exactly changed in the function. This is something I have to spend a lot more time on because right now we only know, now this function is the same as this, and it has changed. But then you still have the two large functions, and you have to pinpoint what part has changed. Have they added an if, and so on. So I have a very broken heuristic right now which tries to find out where the graph structurally changed. And it's mathematically a really, really tough problem because you can't really have a clear definition of how, well, graph similarity would be one thing, but basically you have to find a transformation that would transform one graph into the other. And that's just, I have no clue how to do this right now. I'll have to spend some time on it. Some parts are not quite bug-free or not quite implemented in my plugin. They're being worked on, and ideas always predate the code, I guess, or most of the time. And well, the big thing that is not quite implemented yet is the commutativity thing we had in the last slide, where we're trying to match by going over the match and then to the children, or over the children and then to the match, in order to find the changes in the call graph. That's the thing I will have to add in 2 weeks or so. Okay, so how does this look when we actually go and look at a patch? 1 second. First thing we're going to do is we're going to use the plugin to examine the changes happening to MS-ASN1.dll before and after the EI BR vulnerabilities. So here we have a disassembly of MS-ASN1.dll, and we run the plugin. This is my flaky development version. I just hope it works now. We spawn another instance of the disassembler, which will create all the signatures for the other executable. There's quite a lot of bending over backwards to work with the disassembler. It's quite good in many aspects, but it's inherently single-threaded, and it has certain restrictions that you can't open two disassembly databases at once. So we have to spawn another instance which dumps all the information in the background and so on. Okay. It starts generating the fixed points first by name. Would be significantly faster if I disabled all the debug output, but up until this morning I had to do printf debugging because I couldn't get a debugger to give me source debugging inside the disassembler's process because the disassembler doesn't like to do debugging. And finally got source debugging this morning, so I can move away from printf debugging, which is a big relief. Does the propagation. It's done. Okay, so we have the isomorphism here. We have three windows now. We have the matched functions window, and the functions which could not be matched in either executable either because they were removed, they were changed, or something else went wrong. And we have a limited detection of changes here. So the functions here are the ones that were detected to be changed. Everything above it, here the ones were detected to not have been changed. And we see that most of them are in BR decoding, which kind of makes sense when we look at the security bulletin. And we have changes, for example, in ASN1 deck alloc. So we pop up the two flow graphs, and the code has tried to highlight where the change was. So these are the two functions. ASN deck alloc in the old version, over here, and ASN deck alloc in the new version. And we see the classical construct here, rounding up in the allocator, and then calling local alloc, which can be attacked by a malicious input when you send in a very, very large value, like maxint or whatever. And the rounding up wraps around to produce a zero result. And you can see that here there has been an extra check added that if the rounding up is, like if the rounded up result is smaller than the pre-rounding up result value, then it will return an error. So you can just see that the developers of MS-ASN1 fixed the integer wrapping or the integer overflow in the allocation routine here. And well, the same for ASN1 deck realloc. You can see that my heuristics are broken because in this case the entire function is highlighted, even though the changes are not spanning the entire function. Still have to work on this. But this is relatively trivial to see that, well, when you actually read the code, that they just checked for rounding up, or for the rounding up wrapping. There's a bunch of changes in the deck0 char string. Just as a short explanation, it's how to read those graphs. Those are just the flow graphs consisting of the basic blocks of the function. And loops have been highlighted, meaning a loop entry point is in green. The last node of, or the last basic block in a loop before branching back to the loop entry point is labeled in blue, or is surrounded in blue. Changes are highlighted in yellow with a red border down here. So what's going on here? The old version calls ASN1 dec realloc, and then calls this block down here. The new version seems to have a block added down here. And if we look at it, that all the value, ASN dec realloc, check whether the result is non-zero, branch somewhere. Wait a second. In the old version, they branched up here. Let's follow the green arrow. And then return 0. The new version branches over here, calls another function, and then returns 0. So if you actually look at the function they're calling, they're now calling free, because the old version, when the realloc failed, would not free the original buffer. So that was a potential memory leak if you could get the realloc to fail. And so this is fixing a memory leak. And yeah, that was a fairly nice result. Let's open another one. Now, this is the H323 ASN1 parser, which is part of ISA server. And there was a bunch of PR-related vulnerabilities at the beginning of this year. And this is basically the post-patch version of ISA, of the DLL and the pre-patch version. And I will not run the differ right now. I'll just load save results, because the diffing code itself, because it's such a large executable, will run for 20-25 minutes. So let's see. We have a significant number of unmatched functions in this executable here, 419 to be exact. You might ask why this is the case. Now, cut and paste coders really screw the diffing, because cut and paste coders, people who have the same function just 10 times, obviously create lots of collisions in the signature matching and can't be resolved. This is not an encouragement for starting cut and paste coding, though. So we have 2 functions detected as changed of the ones that could be matched. Ideally, one should now go through the 419 functions which have not been matched and create additional fixed points, because every new fixed point you create manually will allow others to be resolved, and then the changes are propagated. So the idea is to work interactively with the user. Okay, here's the function. Old version to the left, new version to the right. These blocks here have been highlighted. So we see a call to ASN1 per deck alignment here. And then, let's see, where's the corresponding block? This is the corresponding block in the other graph, I think. No, it's not. Let me check something. Well, let's see. This is the part that I still have to work on. Because you kind of have to manually figure out which block is this. So this is the same as this. These two seem to, well, this is the same as this. This is this. Okay. Well, let's just try to zoom in over here. Okay. Okay, so old version calls ASN1 PR decode unsigned 32 value, then calls dec 0 table char string no alloc. New version calls ASN1 PR dec U32 value, ASN1 per deck alignment, and then has an added check here. Deck alignment here, deck alignment here. The new version checks whether the value decoded up in ASN1 per deck U32 value is smaller than 129. So this is the added range check that later on, well, is fixing the vulnerability. let's go over here. Now the interesting part is seeing the second change as well. Which is pretty much exactly the same situation. You have an ASN1 per deck U32 value. This is the same as this. And then a range check after the deck alignment. And then the call to ASN1 PR deck 0 table chart string no alloc. Now, the really interesting thing about this patch is that apparently somebody reported the vulnerability to the product group for ISA server. The interesting thing is that the actual issue was in ASN1 DLL, which was an integer rep in ASN1 PR deck 0 table char string no alloc. But instead of having this bug fixed in ASN1 DLL, it was fixed in the product. There were range checks added in ISA server. With the interesting result that after this patch was published, everybody who looked at this patch had remotely exploitable vulnerability in NetMeeting, because it was not fixed in NetMeeting, and that came, like the fix for that came 3 months later. So the interesting part really is that you're telling people about bug classes in your own code. You're telling people where else they should look when you fix in the product. So you should always fix in the library, quite frankly. And this was one of the fun bugs, because they're fixing one but telling the world about another one. All right. But one more example here. S-channel. At the beginning of this year, there was an overflow in PCT parsing. I hope actually running the diffing process was not a mistake. For some reason, I have this weird habit of always, before I give a talk, I have to change something in the source code and recompile. I'm not sure why that's the case, but all right, here we go. All right. So we got 20 functions which we couldn't match. We got 560 which were successfully matched. And from the security bulletin, we know that the issue itself was in PCT parsing. We have no idea about what PCT is. At least when I received the patch, I had no idea that there is something like PCT. Just the security bulletin gave me the information PCT. I diffed the two executables, and there was one change which had PCT in the name. PCT1 serve handle uni hello. All right. Let's look at the change. They're copying something into a buffer, and then there's a loop here which just takes a byte from the string and knots it and appends it to the end of the string, which is something that apparently has to happen in the PCT protocol somewhere. In the new version, has a range check added before copying the original string into the buffer over here, the compare EBX20. So the old code would just take the string and double it in length and not check for the target buffer to be large enough or for the source string to be sufficiently small to fit into the buffer. The new version does change this. And then it was just a matter of crafting the right input, which I basically did using a graph-based debugger I've built where, you basically set breakpoints on all the basic blocks and start highlighting them when they get hit. And then you see immediately where the code starts deviating in a direction where you don't want to go. And then you can basically, without really understanding the protocol, build input to reach a certain location. So the fun part about PCT was the patch came out, and about 3 hours after we received the patch, we had the IP overwritten. About 24 hours later, we had a working exploit, which was fairly reliable. And this is quite humorous if you look at some German legislation, which forbids any financial institution of installing patches before having tested them for at least a week. So that was the fastest turnover I've ever seen when it came to receive of patch to working exploit. That was a very, very, very short distance. Okay, so what else can you do with the stuff I've been presenting about? To be honest, while diffing security updates might be a fun game, I don't consider this to be the important part about the entire thing. First of all, a friend of mine, Pedro Carrera, who's a Spaniard working for F-Secure, is using this very similar, almost the same approach for automatically classifying newly emerging high-level language viruses. So you can, by measuring how well the isomorphism is constructed, you can automatically cluster related viruses together without having to analyze them all at once. You can just see this is a relative of XYZ virus, which also removes a lot of the ambiguity from naming conventions, because you can very clearly say, this is one virus family, this is another virus family. There's other interesting parts of it. This can be used, or the primary use for it in the future for me is not the diffing, but not only porting function names, but porting names of global variables, meaning porting information from one database to the other. Because I'm oftentimes faced with having to reverse engineer subsequent versions of the same executable. And I'm trying to be able to port global symbols and do all sorts of things in that direction. The other interesting part is I'm thinking it might be quite useful for detecting code theft. Because you don't, like right now, there's a bunch of tools out there that pretend to measure the similarity between two source code files. But I think the executable might be a more concise place in which to measure the similarity. And the big advantage is you wouldn't need the cooperation of the party you accuse of having stolen your code. You can just take their binary and then measure how similar it is to a library you might have and so on. It's quite fun for doing spot the GNU code in commercial software as well. Now, what I will be doing in the next, the next time is, or the things I have to work on is, I need to find a way of better highlighting where the change in the flow graphs are. Because right now, oftentimes, my heuristics break down and then the entire graph is highlighted, or parts are highlighted that are not changed. That's a big issue I have to tackle, and it's not an easy one. I want to improve the porting of global variables, which is probably relatively trivial to do. And then there comes the hard part, formalizing all this, that there's a more solid theoretical foundation for the entire crap. That's something that my university mostly insists on. Well, and once I get it all formalized, I might try to write a Usenix paper about it, but that's, I don't know, we shall see. Yeah. Okay, so you basically just randomly try to associate them and then see whether it works or not? Yeah, but it's a backtracking algorithm or... Okay. Yeah. Well, any mistake I make early on any mismatch initially will yield lots of mismatches later on, and I haven't implemented any sort of detection of a bad initial match. Ideally, I should be able to, or I should try to write something where once I notice that I'm getting a lot of really weird or really strange results, I try to backtrack and see from what result that came.
You treat it as an AI problem.
Yeah, I guess. Yeah. Okay. Oh, okay. Okay.
I think the temperature should start off with the temperature high and you're probability to relate to minus KT, right? And you make decisions early on that are kind of more vital to explore some of the space.
Yeah.
And then you gradually lower the temperature and obviously you've taken some weights from those early simulations.
Yeah.
And then like everything like comes down and you hopefully miss all the local minima because you explored a bit of elevated temperature and then you sink down into a very point.
Yeah.
See like simulated the movie.
Okay.
Using like looking at like heat capacity of like absorption research, they sometimes you fall into these local minima and then will give you stupid results.
Yeah.
So like there's events all around.
To find it. Yeah. Well, it definitely would be an issue. To be quite honest, the risk of making a bad initial match is relatively low if you have names and you have strings. Obviously, the other thing which I'm going to implement relatively quickly is not only having functions as nodes, but strings in the binary as nodes, at least like hashes of the strings, as just normal nodes in the graph. And you can match those, and they're very certain. And it's true that it would be useful to have some sort of backtracking or some sort of algorithm that allows me to undo a mistake I made early on. Or just something that allows me to, for example, the issue with the H323 parser with the massive duplication of the same function. If I would just randomly like flip a coin and take one of them and try to match them and see whether it still pans out later on in the graph, that would definitely be advantageous. But yeah. Well, you have names of imports. You have names of functions that are imported. You have strings, and you have entry points. That's well, people can deliberately want to mislead you, but they can also have to assure that the code remains functional. It's true that actually there's other things you can do very easily to kill this. Basically, patch your compiler to generate a constant number of basic blocks in every function. That shouldn't be too hard, just add knobs. But the issue truly is that I don't see why anybody would have an interest in attacking this directly, because it would just lead to a stupid cat and mouse game where people who actually have to use the software would lose. So yeah. Can I? Okay. Yeah. Looking at functions that don't import anything. Yeah. Oh, well, the disassembler produces a very, very good output. Yeah. Basically, it's heuristics for function prologues. Yeah. And I blindly trust IDA, which is not always correct because IDA screws up. But in general, for x86 executables, there's very little. I mean, there's only so many sensible ways in which you can do a function prologue. So IDA is fairly good at finding these things. Obviously, if you do self-modifying code, I first have to remove all the self-modification before doing the analysis. This is, quite frankly, there's 1,001 way of pushing this over if you want to. But the real issue is, in the end, you still have to have graphs in memory. and they have to be connected there, and they have to execute, and everything you try to avoid having, like, anything you do goes at the cost of efficiency, and is just a useless cat and mouse game at that point, because people, like, when you start self-modifying your code, people will unpack. When you try to create functions that have graphs that create collisions, you forfeit the efficiency of the code because there's only so many sensible ways in which you can arrange the basic blocks. So, yeah, that's why I'm saying it's not necessarily, or the main intent in building this thing was not diffing security updates. It was porting information from one database to the other. And the diffing basically fell out as a byproduct, and it's a lot of fun. I mean, I really enjoy reading diffs because you learn so much about what mistakes people make, and well, you get free O-Day as well. And but it's not really wasn't really the goal. So it's not designed to be resilient to attacks specifically against it. Any other questions? All right, then thank you. Oh, sorry. Yeah. 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 It's definitely true that it would be useful to incorporate the size of the basic blocks into it. I have tried to avoid it so far because I get weird, not weird results, but I get situations where you have functions with the same signature, and they differ by a few instructions, like 4 or 5, but they're different. And then the compiler, next time around, starts breaking up an LEA into 2 additions, and well, you get the same, or get the function size. It would make sense once the difference is large enough to start trusting it. The basic idea, well, anything that would associate things that are likely the same into groups which you can then try to match more accurately would definitely help. The other big challenge is trying to detect changes in buffer sizes, which is definitely important, and then trying to detect changes where somebody replaces a signed with an unsigned value, which is I have no idea how to do this without resorting to translate assembly code into the whole code analysis path, which I was deliberately trying to avoid with this one here. So, any other questions? Yeah. I thought about the branch instructions as well, but the issue truly is that the signedness is not determined by the branch instruction itself, because the branch is unsigned. It's the comparison before. Well, it's jump greater equal and so on. But the issue is that at that point you have sign extensions, move SX, move ZX, which you won't see, and it would also imply that you have to start dealing with very platform-specific things. And the one golden rule I've set myself up front is whatever you do, don't look at the code itself, like at the instruction level. Because obviously I could there's something called flirt, which is basically pattern matching on functions, which works fairly reasonably well. And anything that creates me fixed points would be good. So something like building a flirt engine into this would be a working idea. But I don't know, for some stupid religious reason, I've decided, okay, I'm going to stay away from instructions at all costs, which might or might not be a smart move, but we shall see. Any other questions? It can, but then you have to create your flow graphs differently. Like the current code I have basically just takes the information from IDA, the cross-reference information, and then builds the graph, and it's very, very simple. Once I have conditional execution instructions, I have to start, for every conditional execution instruction, create a new node in the graph and a fake jump, a fake edge. And that's just, it won't be impossible, it's just going to be more work. And it's not the trivial add 3 lines of code and have a new architecture, which I have right now for non-conditional execution. Yep. But the call graph is always growing exponentially with the number of branches, right? So, and I can cluster the ones with the same predicate together. So that would be at one node, and then it would be more complicated. It would definitely, like the generation of the flow graphs would not be trivial. Any other questions? Then thanks.